Good morning, everybody, and welcome to IAS. We have a packed schedule, so we should try and stick to the time. Not everybody is here. There are many other registered people who are not yet here. Hopefully, they will come here at some point. And I think there's no need for a lot of introduction either to IAS or for Subir Sachdev. So I would just call him to the stage.
Great. Well, thank you very much, Nadi. It's great to be at IS as always. Good to see you all. All right, so I'll talk about a recent experiment called the Yamaji effect. And don't worry, I had no idea what the Yamaji effect was either a year or so ago. And I explained what it is. And we'll discuss some of its possible theoretical implications. Okay, so this is, of course, about the cuprates. Where you have an insulating antiferromagnet, you change the density of electrons. This is the density of holes P, and then eventually, of course, you get high temperature superconductivity. The part that's fairly well understood is the regime at large P, where the density of holes as measured from the fill band is 1 plus P. And so if you measure the Hall effect, you find exactly that. If you measure the Fermi surface as measured in photoemission, then you find that the area occupied, the electrons are over here, and the area of this region is 1 minus P, and the area of this region is 1 plus P in units with the total area, of course, is 2. So this obeys a fundamental theorem of solid-state physics, the Lettinger theorem, proved in 1960, that the area enclosed should be the same as that of free electrons. Okay, so that's all well understood. For my purposes, there's another view of this, excuse me. Okay, there's another view of this Lettinger theorem, which was put forward by Oshikawa, which is sort of an anomaly point of view. If you look at an anomaly associated with translations in a global U1 symmetry, you can also establish this famous result. But this is a non-perturbative argument, and as we'll see, it's much more general and applies in many different situations other than a Fermi liquid. Okay, so now the mysterious part is what's happening at small p, where you get some rather mysterious Fermi arcs in photoemission. If you look at the Hall coefficient, it appears that the density of carriers is P, which is the density you expect when you're doping away from the insulator. In this case, the insulator, of course, is not a trivial insulator. It has 1 electron per unit cell. Excuse me. Sorry, just give me a minute. Okay. All right, so measured from the antiferromagnet, there's a density of carriers as P, and that's exactly what you see in the Hall coefficient. But if you look for the Fermi surface, you see something rather mysterious in the pseudogap phase. Okay, so let's jump ahead to the recent experiment published just about a month ago called the Yamaji effect. So this is measured in a particular compound, the mercury compound, which has a very simple crystal structure. It's just the square lattices layered on top of each other. So as a consequence of this, the dispersion along the z-axis is very simple. It's just a cosine dispersion. So if you assume that there's a Fermi surface of an elliptical shape, then you'll get this warped Fermi surface. Now what you do is you measure the resistance of the sample in this direction, while you apply a magnetic field at some angle theta. Now the electron will execute an orbit in momentum space, which goes around this way. And the area of their orbit is what determines the dispersion of the electron in the z direction. Now it turns out there's a very special angle called the Yamaji angle, where this area doesn't depend on the z-axis. So at that angle, there's no dispersion in the z direction, and it's effectively a flat band. So as a consequence, if you measure the resistance in this direction, there'll be a peak. All right, so this Yamaji effect has been studied in various organic materials, and it works extremely well. But so far, it hasn't been seen in the cuprates. And the reason now we understand is that many of the cuprates have a very complicated spectral structure. They all have square lattices, but the structure in the z direction is rather complicated. But in this particular material, this mercury material, which can be made very pure, it's very simple. It's just square lattices directly on top of each other. And so that opens up the possibility, which nobody appreciated before this experiment, of observing this Yamaji effect. Okay, so what did they see? So here's the resistivity as a function of angle, and they see these peaks, which they call the Yamaji peaks. Here's a complete calculation of the resistivity that's the observation, excuse me. That's for different angles phi in plane. And here's the corresponding calculation from a simple Boltzmann calculation, which matches very well. So from this, they conclude that there is a pocket. And the size, moreover, they give you also the size of the pocket. The size of the pocket is 1.3% of the Brillouin zone. So this is quite remarkable. It's really the clearest evidence we have of a pocket rather than a Fermi arc. And furthermore, you're getting an estimate of the size of the pocket, 1.3% of the Brillouin zone. The amazing thing is that there's a formula given by Yamaji, which only requires you to know the angle and the z-axis spacing. And from that information, you can deduce the area of the pocket, assuming it's elliptical in shape, which is what they assumed in this analysis, and that fits the data reasonably well. All right, so that's pretty exciting. And photoemission was showing arcs. It wasn't clear what they meant, but here's an experiment that shows that there actually is a pocket. And that has strong implications for the theory of the cuprates. And remember this 1.3%. I'll come back to it shortly. All right, so now let's do some very simple theory on what happens when you dope a mod insulator and what kind of Fermi surfaces you're going to get and connect them up, hopefully, to the observations. Okay, so first of all, let's just take free electrons, which of course is a picture that works at high doping. And then the density of holes, as I said earlier, is 1 plus p. Now these holes have spin. So now I'm going to actually write the area in units where the total area is 1. So the area of the green region here is 1 plus p over 2. So that's the Luttinger area, and there's no broken symmetry. Okay, so now let's start from the antiferromagnet. This is an insulator, so there's no Fermi surface. But when you dope it, imagine you dope it so that the long-range order still survives. So then what's going to happen, because of the broken symmetry, your Brillouin zone will be halved. And then to figure out the Fermi surface, we just think of free electrons moving in this background. So you put the broken symmetry in your free electron theory, and that's what Luttinger says you should do. And when you do that, you get these 4 pockets. And the total area of the occupied states should be P, because that's the density of holes from the insulator. So that's still part of the Luttinger argument. So how many pockets do we have? Well, this is our new Brillouin zone. So you don't really have 4 pockets, you have 2 pockets, this pocket and that pocket. So you can think of it valleys. There's 2 valleys, and there's 2 spin. The total density is P. Therefore, the area of each pocket should be P over 4. Okay, so that's what the antiferromagnetically ordered metal should have pockets of this area. All right, so now let's think of something more exotic. So imagine you have some kind of spin liquid. So I'm just taking a very simple picture of resonating valence bonds or dimers, and I put in a few holes. So now, as these bonds resonate, these vacancies can move around. And as you can see, the vacancies are moving, they're not carrying any spin. So these objects are charge E and spin 0. So we call them holons rather than holes. And so you get a state where the holons are moving around. Now imagine that the holons are fermions, which is the case in some theories. So the fermions, they must form a Fermi surface. So at this point, you can now apply, you can't apply the Luttinger theorem because this is a non-perturbative state, very different from the free fermion state. But you can apply the Oshikawa anomaly. That should also apply to this state. And so that would say there's a total anomaly of 1 plus p. And this background resonating valence bond liquid gives you an anomaly of 1. And the Fermi surface anomaly is p. And that's how you deduce that any Fermi surface must have total area p. OK, but now, what's the area of each pocket? So let's assume there are 4 pockets. So there are 4 valleys, because there's no broken symmetry, but they're spinless. So the area is again p over 4, as in the antiferromagnet, but for very different reasons. But there's a more serious problem with this picture. These are holons, so they can't really tunnel coherently from one layer to the next to see the Yamaji effect. The Yamaji effect is showing coherent transport in the C direction. So really, there's no way you can get the Yamaji effect with this, although the area is the same as in the antiferromagnet. So now let's imagine a new state. So what we're going to do is now this state can have also spin-on excitations. So you can imagine taking these singlet bonds and breaking them into spin-a-half objects. Now each of these spin-ons carries spin but no charge. These are these arrows here. And it costs you energy J to create a spin-on. But now imagine that the spin-ons all gravitate to a nearby holon. And then the spin-on and the holon form a bound state, which are these green objects. Now, if you notice, there was a lot of hopping going on here. And that gains you some energy to form the bound state, and that energy gain is T. So the simple argument is that these bound states really will always form, because T is bigger than J in any reasonable description of the Hubbard model, say. OK, so you get these states where there are holon spin-on bound states that are the green objects, but you still have the valence bonds, that are the blue dimers, and they can all resonate. And as this thing resonates, these green objects are moving around. So now what do they carry? They carry spin and charge. They get charge E and spin a half, otherwise known as an electron. So this is just an electron with the same quantum numbers, and it can have coherent tunneling along the C-axis. So if you do a simple theory of this, which is, well, there's no, I won't go into the theory very much. It's not so easy to do a complete theory of this. But you can do some numerical calculations. And again, you get 4 pockets. And so what's the area of each pocket? Well, again, there's 4 pockets. So the valley degeneracy is 4. But these are spin-a-half particles. So the total degeneracy is 8. So the area of each pocket should be p over 8. And this could potentially be a candidate for the Yamaji effect, because it also has coherent tunneling on the C-axis. It has no broken symmetry, as the experiment has no broken symmetry. And the area then is p over 8. OK, so this is a state which is an exotic state. And again, it satisfies the Oshikawa anomaly just as in the holon metal. And it also has these spin-on excitations. All right, so the punchline of my talk really is that there are these different areas, and these are the 2 possibilities. This is ruled out because no coherent transport. Either it's some kind of thermally fluctuating antiferromagnet, or it's a quantum fluctuating antiferromagnet, which gives you area p over 8 versus p over 4. And this distinction between these 2 states was already noted in this paper in 2007 with Mike Levin and Senthil and others. OK, so coming back to the data, 1.3%. This is a doping 0.1. So that's very close to p over 8 and very far from p over 4. OK, so there's still a lot of issues. This is not conclusive by any means. We'd like to have data at different p. There's the issue of the quasi-particle residue being not uniform around the Fermi surface. And this is something we investigated in this recent paper. But anyway, even given those issues, if this works out, it's not conclusive evidence, but it's the best evidence we have so far of some sort of fractionalization happening in the cuprates. All right. OK, so that was, I just gave you very simple pictures of this FL star state. But the beauty of the anomaly argument, it doesn't really depend on any of the details. You just have to have a coherent picture of what the excitations are, and it tells you what the size of the Fermi surface has to be. Yes? Correct, correct. Well, I mean, it's a quasi-particle. It doesn't have any extra gauge charges. It's a gauge-neutral object in terms of emergent gauge fields. It just has the same quantum number as an electron. There will be some matrix element, this quasi-particle residue factor that will determine the c-axis transport. So we've been studying some of that. But it's still it's possible for it to tunnel coherently. Yeah. It also should give you some apparent photoemission as a pocket, but it doesn't, and that's really the next part of my talk. Why is it that the photoemission is showing you these Fermi arcs? Okay, so that's perfectly related to what I'm going to talk about. This is with various people at Harvard, and also a collaboration with people in Chennai, lattice gauge theorists who worked with us on this part of the talk. And there's a long review article that I invite you to look at. Okay, so what I want to do now in the remaining 15 minutes, I think I have, is present a real theory. And what is it a theory of? It's a theory of this state. And this state has two types of low energy excitations. One are these green objects, which are fermions forming this Fermi surface. And the other is this orange arrow, which is a spin-on. It's a spin-a-half charge zero excitations. So we want to write down a theory which couples them together. That's going to require a gauge theory because the spin-ons must carry gauge charges. And also you're violating the usual Luttinger theorem. So there's no way around that. So we want to write down some gauge theory for the interaction of these holes, charge E spin-a-half with spin-a-half charge zero. Okay. All right, so the way to do this microscopically is what we're calling the ancilla layer model, which was proposed by Yahui Zhang a few years back. And we've been working with it quite a lot in the intervening years. But I'm not going to go into the details of this model because the benefit of hindsight, you can actually derive everything by kind of waving your hands and using symmetry arguments, so which is what I'll do here. Okay, so first thing, we need a theory for the two ingredients in the state. One is the hole pockets, and the other are the spin-ons. So for the hole pockets, since these are just electrons, we can write down some electron Hamiltonian. So the electrons themselves, C, have density 1 minus P. But if you add in another ancilla fermion, F1, with density 1, then the total density of fermions becomes 2 minus, electrons becomes 2 minus P, which is the same as minus P, because everything is mod 2 for spin-a-half electrons. And so this kind of hybridized theory, with this hybridization phi, is just a number now, will at zeroth order give you pockets. And as you'll see, there's a kind of a very intriguing connection to the Weinberg-Salam theory of weak interaction. So this is, you know, there, of course, you'll write down Dirac fermions as electrons. Here is a more complicated electron Hamiltonian with these pockets of size p/8. Okay, so that's ingredient number one. Ingredient number two are the spin-ons. So which spin-on should we take? So here I'm going to rely on a lot of recent numerical work, which has started converging on a state that really goes back to Affleck and Marston. It's just a state of spin-ons, which are fermions moving in pi flux on the square lattice, coupled to an SU2 gauge field, lattice gauge field called U. So you can write on a very simple effective action for it. That's the next slide, where they have some hopping J on a square lattice, which has pi flux on each plaquette. I choose to have an imaginary hopping here because that's the gauge in which the coupling to the SU2 gauge field is simplest. It's just the usual minimal coupling for these Nambu type fermions. So this action also has an SU2 spin rotation symmetry, which is not evident in writing it in this way. Okay, so if you take the low energy limit of this theory, then you get a theory of SU2 gauge theory coupled to two flavors of Dirac spin-ons in 2 + 1D. Another curious fact is you just change all the 2's to 3's, you get the QCD of the light quarks. Anyway, so now this is a confining theory in 3 + 1 dimension. And the latest numerical evidence of this is also possibly confining at the longest length scales, but the length scales are long enough that for quite an appreciable distance, you can just think of it as some conformal field theory, which is what I'm going to assume. Okay, then finally, you have to couple these two sectors together, the holes and the spin-ons. And so this you can write down just by gauge invariance. And really, you have to introduce then a charge Higgs field B, which is a SU2 fundamental. And you get a Yukawa coupling between the spin-ons and the electrons. And I forgot to mention that you can think of the spin-ons as analogous to the neutrinos. So this is the action of the bosonic sector. You have these bosons, which also move in pi flux, and Maxwell term for the SU2 gauge field. And finally, this is the Yukawa coupling between the electrons, the spin-ons, and the SU2 gauge field. So this is the theory we really have to study. There's also quartic potential for B that I won't write out explicitly. So it looks rather messy, but the ingredients are kind of forced on you by the structure of the pseudogap state. Okay, so there's various simple things we can do with this. So what we did was, so here's it written out again. What we did was to just look at, first of all, think about it perturbatively. So imagine the state is stable down to 0 temperature. Then you have, on the fermionic sector, you have these hole pockets with anisotropic quasi-particle residue. You have the spin-ons, which these are the 2 Dirac spin-ons on these 4 points. And then there's some coupling between them. But what you notice is that they are in different regions of the momentum space. And the Higgs boson here is gapped in this FL star state. So in fact, this whole structure is quite stable if the FL star state was stable down to 0 temperature. But we now imagine that actually it's not stable, but it's going to undergo a phase transition as you lower the temperature to superconductivity or charge density wave or something like that. And so you can address that in a Born-Oppenheimer theory. So this is where the lattice gauge theorists come in. What you do is you take all the bosons, which are the analog of the nuclei in Born-Oppenheimer, which are the Higgs field and the SU2 gauge field, and you just do a classical thermal simulation of that. And in each background of the thermally fluctuating bosons, you diagonalize the fermion Hamiltonian. So when you do that, you find exactly the kind of structure you see in photoemission. The backside of these pockets disappear. The spin-ons are, of course, not visible in photoemission directly. And this is, presumably quite similar to what you see in the experiments in photoemission. Now, you might worry that this kind of damage to the Fermi surface by thermal fluctuation is going to destroy the Yamaji effect. So to address that, we looked at quantum oscillations in this thermally fluctuating state. We can't quite compute the Yamaji effect, but we can compute oscillations in the density of states. And we definitely find regimes in which the Fermi surface is an arc, but nevertheless, you see oscillations in the density of states, showing you that, in probes that don't eject electrons from the sample, there still is memory of the Fermi surface that preceded the arc, but was washed out by thermal fluctuations. R is a Landau parameter in the boson action. Where did it go? There, that's R. Just the mass of the boson. It's a tuning parameter for how far you are from superconductivity. At 0 temperature, it's condensed. So I'm going to show you some pictures of of the superconductivity in a minute. So let's see. All right, so in this framework, we treat the bosons classically. You can work out the zero temperature phase diagram very easily, just a minimization of the boson energy functional. And you get all kinds of states with charge density wave order of various types. But most interestingly, you also get a D-wave superconductor, a big part of the phase diagram. And this is the fact that it's a D-wave superconductor is closely connected to the fact that you started from this pi flux spin liquid. All right, so now, so this is the state at zero temperature. And now you can raise the temperature a little bit, and you see thermal fluctuations. And in that thermally fluctuating state, this is from the lattice gauge theory computation, you can measure the phase of the superconducting autoparameter. And what you see are these vortices with the phase of the superconducting autoparameter winds by 2 pi. So these are vortices of flux h over 2e of a 2e autoparameter, even though the boson you're working with in the gauge theory is charge E. So this is, it's really confinement induced by the SU2 gauge field. You really have to put in fluctuations of the SU2 gauge field to get the structure properly. And even in this computation here, we did put in the fluctuations of the SU2 gauge field. Okay, so you get these vortices here. And if you look at some kind of density variable in this picture here, this is the same snapshot. You see these very interesting structures in the core of the vortex. If you zoom into this, well, okay, you see these modulation. Of course, we chose parameters with the modulation at period 4. And that's to mimic, what's seen in STM experiments, going back to this early work of Hoffman and Davis, where the vortex core, you had these period 4 modulations. You can also start from this state and raise the temperature and measure the helicity modulus of the superfluid density. So then you see a Nelson costless Thouless transition at some temperature. And this is the Nelson costless line for a charged 2e autoparameter. So in the end, it's a conventional superconducting phase transition of a 2e autoparameter, but it's written in a theory which has charge E and an SU2 gauge field. And that's really important for us to be able to compute the fermion structure. You can't do that if you just write down an effective theory of the charge 2e autoparameter. Okay, so I have 2 or 3 minutes. So now let me put this in some perspective for the full phase diagram. So I've been talking so far about this FL star state, where I had this hybridization phi that gave you the small pockets from the Fermi surface. So now to get the race to the phase diagram, to get the large Fermi surface, I have to really set the phi to 0. So to get the global phase diagram, I have to really take this phi object and also elevate it to a dynamical field. So that gives you a more complicated theory, which I'm not going to write down. I presented the theory really in this limited regime where phi is just a constant. But anyway, that sets up the possibility of a transition at 0 temperature between the small Fermi surface state and the large Fermi surface state with a strange metal in between. And this is another transition we've studied a lot. And here in the presence of disorder, there's a Yukawa SYK model that matches many experimental observations. However, in the real world, this phase diagram is too general. What actually happens, as I just showed you, is that there's superconductivity at 0 temperature. So this phase transition, which was present in this hypothetical FL star state at 0 temperature, disappears. So in fact, a key point here in the whole construction is that the superconducting state you get here from a BCS transition is the same as the state I've just described from the FL star theory, which is a confinement transition of this SU2 gauge theory of the pi flux phase. And they give you essentially the same superconductor, which is smoothly connected. So there's no actual phase transition here, which is consistent with many observations. And so it's just a BCS state in many respects, except in the center of a vortex. What's not true, I mean, it's a BCS state, and this is a BCS transition, but this is not really a BCS transition as far as the fermionic sector is concerned. It's much better described as a confinement transition of SU2 gauge theory, and that allows you to then describe the Yamaji effect that I began my talk with. Thanks.
Just a basic question. So since this effect depends on the z direction derivative of the Fermi pocket size, how could it be independent from the details of the z direction component? Like I just know
yeah, so that's what we've explored in this particular paper, and there are small changes, but the basic difference between the SDW and the where's the paper? Yeah, so this paper here just came out in the archive this week. That's precisely the issue we explored. So yeah, you're right that the Yamaji calculation and also the calculation in this experimental paper is a bit too simple, because they just assume that the tunneling amplitude in the z direction is the same around the pocket. And that's not true. So we used the Ancilla framework to make the tunneling anisotropic. You know, we didn't do the full SU2 gauge theory for that. That would be rather difficult. But we could still see that the results are more consistent with the Yamaji, with the FL star state than the SDW state. You know, I would say that just the fact you're seeing these oscillations tells you there's a pocket. That already is a big thing, that there's such conclusive evidence, I believe, for a pocket. And now you can argue about the area. And, you know, the SDW state is not at all reasonable because there is no magnetic order seen in any state. So, yeah, okay. I don't see what else it could be, but okay. It'd be interesting to see if there's any other explanations of these observations.
But the last slide, so
Yeah.
these transitions, I assume they're all first order, right?
Which conditions? Well, zero temperature. This one? Well, so this is just a costless, Thouless transition ultimately in the sense of universality. And it's smooth all the way across. But if you want to describe finer details other than the universal properties, like what's happening inside a vortex, what's happening in photoemission across the transition, and then you would use very different theories on the two sides. On this side, you would just use BCS theory. It would do quite well. In the vortex, you get this peak, subgap peak called the Wang-McDonald peak, and you see that on this side. You don't see it here. The photoemission, as you can see, looks completely different. So if you want to describe, say, how does the photoemission change across the transition, these are features at all momenta, not just the longest scales, or in the site of a vortex. You use very different theories. But if you measure the jump in the superfluid density, that will be Nelson costlets all the way across.
Genuine transition.
Well, it's a costless, Thouless transition. I'm calling it confinement because that's the physical picture I have. But in the formal sense, it's just costless. Thouless of charge 2e boson. That's all it is. That's the universality class for a field theorist. But if you want to do a bit more and understand the electronic structure or the vortex, then you have to do much more. And the framework of the SU2 gauge theory is what allows you to do that. Yeah.
Your capital B boson, that's charge E or charge 2E?
Charge E. Yeah.
And so it's by virtue of coupling to Yukawa coupling to the Fs and
No, so that's actually brings up another important point. So there's a charge E boson here, which is this boson here. Yeah, so this boson here is an SU2 gauge it's an SU2 fundamental, and it also has a physical charge E. There's a composite of them which forms by confinement, meaning you get a two boson composite which is formed by the SU2 gauge field. Now, if you do something different where you say, okay, you've got these pockets, let's just pair the quasi-particles in the pockets and get your superconductor. And that gets you the wrong state. That does not get you a BCS state. That gets you a state with 8 nodal points and spin-on excitations and so on. So that's kind of why I'm calling it confinement. It's really the confinement of the bosons due to the SU2 gauge field. So, I mean, this goes back to a physical picture from the very earliest days by Anderson. If you look at this state, you can think of the superconductivity coming from here in 2 different ways. You can take the green objects and pair them. That's the wrong thing. In fact, the green objects are gauge neutral. They're not going to pair that easily. That gives you the wrong state. But the picture of Anderson was that you already have these singlets in the spin liquid. And if you could just get them to be a bit mobile and condense, you'll get your superconductor. And that picture is closer to what's happening. The B is not really a particle, it's just a thermally fluctuating zero frequency field. It's a thermal object. And it doesn't really exist that well because it's really, if you look at any, you really have to do the full lattice gauge theory of B. Sure, yeah, it goes back again to the very earliest days. I think Fradkin had a paper where he first introduced it. It was also used by Li and Wen later on. But no one really, it was with the help of the Ancilla model that we could do a very well-defined and fully self-consistent SU2 gauge theory for all of this. Correct, correct, it's B squared.
Yeah, quick question. You did this Fermi quantum oscillation calculation, including the thermal fluctuations.
Yes, yes.
So is there some correction beyond Lifshitz-Kostovic that could tell you about these thermal fluctuations in the amplitude of the quantum?
We haven't thought about it, yeah. Yeah, it was done numerically at this point, but yeah, it'd be good to do more on that, yeah. Yeah, I mean, the quantum oscillation is the most stringent test than Yamaji. Yamaji doesn't really require full interference as you go around the pocket. But, you know, what we should really do is take many layers and do the SU2 gauge theory with tunneling between the layers. And that seems very hard. Haven't done that yet anyway.